Very good afternoon, dear students. In the last class, we had talked about the basic concepts of Laplace transform. We had seen the definition of Laplace transform and its inverse Laplace transform. We had seen the significance of Laplace transform in circuit analysis. We had seen why Laplace transform is so useful for circuit analysis and otherwise also for from engineering point of view. We had also seen uh, the Laplace transform derivation for some simple functions, like we had seen for unit step function, then impulse function, then your ramp function, and the last one was exponential function. So once we are through with that basic definition part, today we will talk about the properties of Laplace transform. So students, from examination point of view, if I tell you that you should know about the properties of the Laplace transform as well as their proofs. So those proofs, they are required for your understanding as well as you can say from examination point of view. Otherwise, for solving numericals, the proofs of Laplace transforms are not that mandatory, but it will enhance your understanding if you do the complete proof of the properties of Laplace transform. So I'll also talk about some proofs of some of the properties of Laplace transform, and some of the proofs I'll skip, keeping in view that those are not important uh, from your understanding point of view. Okay. So if there is any problem, you can discuss that thing with me later in the class. Fine. So we start with the properties of your Laplace transform. So here are the properties. The first property that we have for Laplace transform is linearity property. So you can call it as linearity property, or sometimes you also come across the term linearity theorem. Okay, you all know the definition of linearity. We have also talked about it earlier also. So linearity implies, or it incorporates superposition in it. So same kind of thing is here. If we have two functions in time domain, one is f1t and f2t, and we want to find out the Fourier transform of the sum of those two functions. Okay, so according to linearity theorem or linearity property, their individual Fourier Laplace transforms will also be uh, the sum of individual Laplace transform. In a way, let me explain it more clearly. If the Laplace transform of f1s, f1t is f1s, okay, and if Laplace transform of f2t is f2s, so we are aware of, you can say, f1s and f2s, and now we want to find out the Laplace transform of the sum of these two. So we can straight away say that the Laplace transform of that combined function will be the sum of Laplace transforms of individual functions. Okay, you can understand linearity in that way, and this will be clarified from one numerical also, or when you solve numericals related to circuit analysis, this linearity theorem will be very commonly employed. Okay, so its proof is also very simple. We have put ft as f1t plus f2t. Rest is the definition of your Laplace transform. So we can separate the two integrals. This is nothing but f1s and this is f2s. So Laplace transform of f1t plus f2t gives us f1s plus f2s. So very simple one. Next important property is frequency shifting property. So students, let me tell you one thing. We all know that your time and frequency, they are opposite of each other, or a kind of duality exists in both these parameters, time and frequency. So if you do something in time, so some equivalent effect is observed in frequency. Similarly, if we do something in frequency, same is the case with time. So the way we have frequency shifting property, in the same way we have time shifting property also. Okay, so let us first talk about frequency shifting property. According to this, why are we calling it as frequency shifting? You look at the solution. Your solution is f of s plus a, and I told you yesterday s is a complex frequency and a is a constant. So it means something has been added to a complex frequency. So it means frequency has changed or frequency has been shifted. So that's why we call it as frequency shifting theorem. So if we want to change the frequency or shift the frequency, so in time, the time domain function need to be multiplied with e raised to power minus at. Let me repeat. If we want to change the, or if we want to shift the frequency in the time domain, we need to multiply the time domain function with e raised to power minus at. Okay, and this can be proved as shown below. So we will take the Laplace transform of e raised to power minus at ft. Okay, so if we substitute this thing in integral equation, then you can see here both the exponents can be combined together. Okay, so we know the definition of Laplace transform. See on the left hand side, whatever we have in the exponent, that comes as the Laplace transform. So here in the exponent we had e raised to power minus st. So this s came here. So here you see, I think there is some mistake. T should come here. Okay, so we have e raised to power minus s plus a into t. So apart from minus and t, we have s plus a. So in the answer, we will get f of s plus a. So this is our frequency shifting theorem or frequency shifting property. And in Fourier transform, you must have come across this property also. So this frequency shifting is also known as modulation theorem in Fourier transform particularly. But in Laplace transform, we call it as frequency shifting. Okay, next. So next we have time shifting. So here what we do, we shift our function in time. So see, here we have ft. This ft has been made ft minus a, means we have shifted in time. Okay, this is nothing but a unit step. So if you put this thing in this integral equation, this unit step is just arrived at in the form of your limits of integration. So we have e raised by minus st f of t minus a. There is one point here. Since f of t minus a is multiplied with u of t minus a, if we draw ut, your ut will be drawn like this, that it will start at t equal to 0. And if you have ut minus a, your ut minus a will be represented like this one. Okay, so this is a, this is 0. So this is your ut, this is your ut minus a. So in this case, your unit step function is also shifted in time and it is starting at a. That's why if you carefully look at this thing, that if you are removing this ut minus a, then your limits of integration has been changed from 0 to a. It is now from a to infinity. And from 0 to a, obviously it is zeros. That's why it doesn't have any significance. So once we have done that, then we will introduce one new variable, that is tau equal to t minus a. We substitute this thing here, and limits of integration will also change. So we have integral from 0 to infinity f tau d tau, and here we now have e raised by minus s tau plus a. So here it was t, t has been replaced with tau plus a here. Okay, and as I told you in the previous slide, whatever is there apart from your t and minus sign, it will come out to be in the answer. So what we have, just a minute here. So students, if we look carefully here, we have e raised to power minus s tau plus a. If you open it up, you'll get e raised to power minus s tau and into e raised to power minus sa. And e raised to power sa is not related with integral tau. So that's why it is coming outside. And whatever you are remained with inside the integration, that is nothing but your fs. So this is your time shifting theorem. So students, try to observe this thing, that you have shifted in time. In frequency domain, what is happening? Multiplication with exponent is taking place. Whereas in the previous theorem of frequency shifting, you were multiplying time domain function with an exponent function. Okay. And what was happening in time domain, sorry, frequency domain, it was shifting. So this is the kind of duality that you need to observe, that if you multiply with an exponent function in time, there will be shifting in frequency. If you multiply with exponent function in frequency, there will be shifting in time. Okay. So that is one thing that you need to notice here. Another important thing that you need to notice here is you have t minus a. So here you will have e raised power minus as. So minus here, minus here. Okay. Look, observe this thing carefully. Minus a, minus a. Okay. Whereas in case of frequency shifting, this was other way around. You had minus a here and you have plus a. Okay. So if you put e raised to power plus a here, you will get minus. So in frequency shifting, it is the reverse or the other way around. Okay. So you must look at these things carefully if you want to avoid any problem while solving your numericals. So as I told you, this is a time shifting theorem, and it simply states that if your time function is delayed by a time a is greater than 0. So t minus a means you are delaying. See, we have delayed this unit step. Okay. Then the result will be the multiplication by e raised to power minus as. If you advance in time, had it been t plus a, then in this case here also we would have got the plus as. So mathematically this thing will take place in case of time shifting, minus to minus, plus to plus, whereas in case of frequency shifting, plus to minus and minus to plus. Okay. Students, our next property is differentiation in time. So in every theorem or every property, you have to keep in the mind that you are given this thing. This thing is given to us, that the Laplace transform of ft is fs. Then what will be the Laplace transform of differentiation of ft? That means dft by dt. Okay. So the Laplace transform of dft by dt will be this one, s of fs minus f0 plus. So students, if you look at this thing carefully, that means that once you differentiate ft, your Laplace transform will be multiplied by s, then minus f0 plus means this is your initial condition. Carefully observe that this f is capital, whereas this f is small. Means this f0 plus is nothing but your ft, where your t has been substituted as 0 plus. So in a way, this is nothing but the initial value of this ft. Okay. So if you have been given some function ft, you are already aware of its Fourier transform fs, and then if you want to find out the Laplace transform of this ft, I'm sorry, I'm again using the term Fourier transform because uh, that has come easily on my tongue. So please assume that Fourier is nothing but implied here as Laplace. So though I am trying to make it a point that I call it Laplace transform. Okay. So if we are aware of the Laplace transform of ft as fs, then the Laplace transform of differentiation of that function will be this one. Okay. So we will also look at the example of this in the later slides also. So now if we want to observe its proof, then this is the equation of your Laplace transform. What we have done, we have substituted dft by dt in our integral equation. So now we have two time functions under integral. So obviously we'll be doing integration by parts. Integration by parts you are very familiar with. You'll identify first function and second function. Okay. So what we have done, your first function you have taken as e raised by minus st. Okay. So what we do, first function, then integral of second function, then minus under the sign of integration. Okay. Your second part of your integration. Okay. So if you apply integration by parts, this is what you will get. So what you have here, look at this thing carefully. This second part of integration by part, it will give you sfs. S has come out, and this is ft raised by minus st dt. This has become fs, and this one is nothing but this one, f0 plus. See, if you put infinity, this e raised by minus st will be 0. Okay. Then if you put 0, e raised by 0 will become 1, and this will be f0 plus. Okay. So this is what we will get here. Fine. So this is your differentiation in time. So students, after discussing differentiation property, now we move to integration property. Okay. So look at this theorem or this property carefully. As we have discussed in the previous slide, that we are aware of the Laplace transform of ft as fs. This is given to us. Now we need to find out the Laplace transform of integration of ft. So you can see clearly here that we are trying to find out Laplace transform of integral f tau d tau. So if we integrate ft, what will be its Laplace transform? So students, I have not uh, explained the Laplace transform proof for this integration in time theorem, because that is a bit involved proof that will not add much advantage to the solution of our numericals. So that's why it is being skipped. So you can memorize it this way, that if you find out Laplace transform of integral, then it will be fs by fs, and this is nothing but this is the, in a way, initial value of the circuit divided by s. Okay. So if you compare this with differentiation property, in differentiation what was happening, your fs was multiplied with s, whereas in case of integration your fs is divided by s. Okay. And f tau d tau has been integrated from minus infinity to 0, means whatever is happening in the circuit prior to 0, that thing is coming here. Okay. So that condition, it will be some constant value, that condition has also been divided by s. So integration means divide by s, and differentiation means multiply by s. So if we leave apart the initial condition part or the constant part, in otherwise in integration you will divide fs by s, and in differentiation you will multiply. Okay, so it is important now to correlate this integration property with the equations that we have learned with regard to our inductor and capacitor. So here I have taken the example of capacitor equation. We know that for a capacitor, the governing equation is IC is equal to C dV by dt. Okay, and if we want to find out its voltage value, the V will be 1 by C integral I tau d tau from minus infinity to tau. So this is the equation for voltage, and this is for current. So voltage will be the integral of current. Okay, and now if we split this thing, split the integral from minus infinity to 0 and 0 to t, this is what we get: 1 by c 0 to t I tau d tau, and your minus infinity to 0 things become your initial condition, initial voltage, that is V0. This is what I have just told you. So if you see here, this V0, this is a constant value. I told you in the previous class also that if you find out the Laplace transform of some constant, it will be nothing but divided by your S. Okay, and here this is nothing but, this is integral equation. This has become 1 by C into IS by S. Okay, so you correlate this thing with this equation, you'll be able to correlate it directly. So your voltage across capacitor will be, here it is, we have Fs, here we have Is by S, 1 by C plus V0, this is the initial condition, divided by S. So you can memorize these things also, and later on when we discuss circuit analysis using Laplace transform, this will be more clearly defined to you. Okay, or more clearly explained to you. So this is how your integration theorem is correlated with your uh, capacitor's governing equation for voltage. Okay, so we move forward. Then another important thing in Laplace transform is initial value theorem and final value theorem. So students, this initial value theorem and final value theorem is very, very important with regard to our inductive and capacitive circuit. And in transient analysis, very wellfully we have described all these things. We know the initial state and the steady state in case of inductive and capacitive circuit. So it is because of these theorems you are in a position to apply your concept of Laplace transform to circuit analysis. Okay, so your initial value theorem gives you an opportunity to find out the initial value of your time domain function. So that is f0 plus, small f means time domain, and if you have capital F, it means you're transformed either in your simple frequency or your complex frequency. So this is also one important point that you should look into. If you come across small case, that normally means time domain, and capital implies your frequency domain. Okay, so if you want to find out initial value, what you have to do, you have to simply multiply the Laplace transform with S, means you have to make S Fs, and you have to substitute limit S tending to infinity. This is known as your initial value theorem. For initial value, you have to make S tends to infinity. Okay, this is another way of representing this, that in time you are making your limit tend to 0, whereas in case of frequency your limit will tend to infinity. Again, the same kind of thing I told you, that there is reverse relationship or dual relationship between time and frequency. So it is evident again here that your time tends to 0 and frequency tends to infinity. In case of final value theorem, that is if you want to find out the steady state of the circuit, steady state means your t will tend to infinity. So if your t tends to infinity, as I told you, you can easily guess this thing that your s will tend to 0. And this SFS is same here in case of initial value and final value. All that is different is whether you have to make your limit of s approach to infinity or 0. If s tends to infinity, we call it as initial value theorem. If s tends to 0, we call it as final value theorem. Okay. So after this initial value and final value theorem, let us now move forward. These are again the summary of whatever thing we have discussed till now, but with the help of this table you will be able to more clarify yourself with the operations that we have discussed. So this addition is nothing but the linearity property. So here you can see that if you are adding two functions in time domain or subtracting, that is plus minus, your fs will also be added or subtracted together. If you are doing some scalar multiplication, means your time domain function is multiplied with a constant, then your Laplace transform will also be multiplied with a constant. Then differentiation means if you are differentiating your time domain function with time, in frequency domain, what will happen? It will be SFS minus F0, as we just discussed. So we have discussed only first order differentiation. Your differentiation could be second order, third order. Though in your numericals, you will very rarely come across this thing. But just for your knowledge sake, this thing has been covered here. So if you are doing double differentiation, this will be the equation. That is S square Fs minus SF0 minus F dash 0. Okay, this is very clear. Similarly, your third order differentiation, S cube Fs, S square F0, S F dash 0, F double dash 0. So you already know dash or double dash means this is also your differentiation and double differentiation. Similarly, your integration. So if you have integral function in time, then in frequency domain, it will be Fs by S. Okay, so this is for 0 to infinity. And if you have from minus infinity to t, this will be Fs upon S. You'll have this initial condition value thing present in your expression. Okay, so students, I will advise that all of you have understood the proof of these properties of Laplace transform. You also try to memorize these operations so that it doesn't consume much time when you solve your numericals. Okay, so this is your time shifting. I'll come to convolution just in 2 minutes. Time shifting, as we just discussed, that if we have ft minus a, then the frequency domain function fs will be multiplied with exponential function. Similarly, in frequency shifting, we have to, in order to obtain shifting in frequency, we need to multiply time domain function with exponent function. Okay, then another important operation is scaling. Means instead of ft, you are doing fat. Your time domain variable is scaled. So in that case, this is also very, very important. I would basically advise you to prove it yourself. It is simple, just integration concepts are required. So what you are doing, you are multiplying in time. So it will be division in frequency. At will be replaced by S by A in frequency and 1 by A outside. This is also very, very important. You memorize this concept. Initial value theorem, we have already seen that F0 will be S tending to infinity. In case of final value, your time tends to infinity, your frequency domain tends to 0. Okay. Now, one more advantage of transform approach is the convolution. All of you have studied convolution in time, and you all know that convolution is a complex operation in time. So if you define convolution, you define it like this. If there are two functions xt and yt, and you want to obtain its convolution, you define it like this: integral x tau yt minus tau d tau. This is how you define convolution, means a complex integral operation. Okay, whereas if you obtain that convolution or transform that convolution in frequency domain, then it will be simple multiplication of their corresponding Laplace transform. So if you have f1 whose Laplace transform is f1s, if you have f2 whose Laplace transform is f2s, and you are convolving f1 and f2 in time, then in frequency you need not do anything, you simply multiply f1s and f2s. So whatever operation which was very complex in time, it has become simple multiplication in frequency. That is one of the biggest advantage of using transform approach, whether it is Laplace transform or your Fourier transform, that convolution in time becomes multiplication in frequency. Okay, so these are the main operations of your Laplace transform. Now we move forward. So these are the Laplace transform pairs that I have shown you. In fact, I'll advise you people that you try to find out Laplace transforms of all these functions which is given to you. This is a homework for you people. You may find their solutions also in your mathematics book. You may try integral expressions of Laplace transform and you will very easily find the solution. Okay, this way you will be able to practice the solution of or obtaining your Laplace transform pairs. So you can take a snapshot of uh, this table so that you can work out these functions at your home. Okay, so some things we have already covered here. We have also discussed this is impulse function, this is unit step function, this is your ramp function. This we have already discussed. You have also discussed exponent, and see, this is nothing but this is a generalized representation of your ramp. Here we had t, and here we have t raised power n minus 1 divided by n minus 1 factorial. So these are, you can say, equivalent or generalized version. Fine. So here what you are doing, you are simply applying a theorem here. Okay, you know, this is your exponential function, you are multiplying it with t, so some property will be applied here. Similarly, this is also the generalized one of this one only, and you are able to apply property here also. So here I want to tell you that how will you find out the Laplace transform of sine omega t. So it is very simple. You will have to represent sine omega t in the form of exponent, that is your e raised to power minus j omega t, sorry, e raised to power plus j omega t, then minus e raised to power minus j omega t, okay, and divide by 2j. So you have to represent your sinusoidal function in this form. Then it is nothing but you have to obtain Laplace transform of exponential. So some linearity property will be applied here, and the result of Laplace transform of exponential function will be applied here. Similarly, you can also directly obtain Laplace transform of cos omega t. So for cosine, you will represent again in the form of exponent, that is e raised power j omega t plus e raised power minus j omega t divided by 2. So if you do that and apply linearity property, you will come across this thing. Okay, there is one more way. As I discussed earlier, if you apply differentiation property to sine and cosine, you will also be able to obtain their corresponding Laplace transform from each other. So differentiation property, integration property can also be applied. Okay, so here we have introduced one more term, that is your theta. Okay, so if you do that, this will be the answer. So here you will have to apply your trigonometry concept, that is sine omega t plus theta. You'll have to solve this by using sine A plus B. Similarly, you have cos omega t plus theta. Then uh, once you are aware of the results of sine omega t and cos omega t Laplace transform, you can easily obtain this e raised by minus 8 alpha t sine omega t. So you will again apply property and this will be the answer. So students, you have to go through each and every Laplace transform pairs shown here. These are all important transform pairs which can be directly utilized in numericals also, and that will also help you in practicing the solution of your Laplace transform. Okay, so please do that, do practice these so that you are perfect in solving your Laplace transform pairs. Okay, so this is homework for you, and this is one example which will explain that how can you obtain Laplace transform. So here it is 2 times u of t minus 3. So you can directly obtain its Laplace transform by using integral equation. So you can see here that ut minus 3, it is defined from time t equal to 3. That's why your limit of integration has become 3 to infinity, and 2 is a constant which comes out. Ut is nothing but 1. So this is how you get this equation. If you solve this and substitute the limits of integration, this will be the answer. Okay, and there is another way to arrive at this solution, which is very, very simple. Just by using the property, we know that Laplace transform of ut is 1 by s. Okay, now we will multiply this ut with 2, means we are multiplying with a constant. Then its Laplace transform of 2 times ut will be nothing but 2 by s. Okay, now you see here we have 2 is there, we have ut minus 3, this is ut, but t minus 3 means we are shifting in time, so we will apply time shifting property. So if we apply time shifting property to this one, that is we make it u t minus 3. Okay, that means we have applied time shifting property. So if you apply time shifting property, as I told you, if we shift in time in frequency, it will be multiplied with exponent. Okay, so it will be e raised to power, since it is minus 3, we will have minus 3 here also, we'll have minus 3s. So this is multiplication of exponent with the original result, that is 2s, sorry, 2 by s. So 2 by s. So same answer. This is the beauty of using properties of Laplace transform, that we have obtained answer to this question by using integral equation and also by using time shifting property. Fine. So then we move forward. This is another example which shows you how to apply final value theorem. Okay. So students, we stop at this point, and we have seen a few applications of some of the properties of Laplace transform. We will continue in the next class.